Hi, I'm Bob Doyle, coming to you from my ITV studio in Cambridge, Massachusetts, where I'm webcasting regular lectures on information philosophy. Information philosophy is the first new method of philosophizing. Let's see, I want to do this. It's a new method, and actually it's since the early 20th century, when logical positivism and analytic language philosophy were dominating and are now being used in all the major universities in the English-speaking world. There has been very little new in the way of a systematic philosophy, a philosophy that tries to talk about all the problems of physics. And my argument is that information philosophy has the capability of being a systematic philosophy. I know that's ambitious, but where language philosophy wanted to cut back a little bit on getting into questions that seem beyond words and arguably couldn't be dealt with by just talking about them or arguing about them logically or arguing about them in terms of getting all our concepts right, getting the definitions of right, so that then anything that followed from proper complete definitions would give us, quote, truth and so forth. Even though they had an empirical idea of some of their things, they talked about knowing that things were the case by verifying them. That was a very important notion around the 1920s. Went on for many years, that one had to do experiments to make a connection between our language, our words, and the way the world is, the way the natural world is deep down. And certainly when quantum theory came to be discovered, it put a wrench in a lot of those plans, because philosophy had arguably been a kind of laws of nature discovery. And though most philosophies in ancient times, from the time of the Greeks, had been an attempt to know the world, understand nature at its base, and therefore understand what we're doing here and so forth. The 20th century and the late 19th had gone away from this idea of thinking about metaphysical problems, or what the positivists of the 19th century called theological problems. The idea was to cut back and stay discussing things that we could somehow verify, talk only about things that we felt we knew something about. For example, we could talk about our behaviors, but we couldn't talk about what's going on in our mind, because although we can introspect into our mind, we couldn't really see into others' minds. Each of us can see inside our own minds and hope that we're doing something that's like others are doing. Those raised questions about the technique of philosophy and the idea that it could systematically explore everything. They put walls on things. Don't look there. Don't try to look past your perceptions into the things themselves. It was a war cry for many years that we cannot access the things themselves. Now, in that case, we're talking about, for example, maybe the atoms. Although today we pretty much can see atoms doing their thing right at the atomic level with our wonderful electron microscopes and other beautiful technical tools. So they were wrong about that. We can get to the things themselves in an important way, get information that's in the things themselves and put it into our minds and think we understand the world. And that's why I want to move beyond the language philosophy, logical philosophy, and the limits that were put on that, limits on knowledge and so forth, limits on reason even was described, and we need to put limits. I'm saying I'd like to take the limits off and develop a philosophy called information philosophy, which is just to think about what is the information in the structures in the world that we're trying to understand. And most of those structures are passive structures, I call them. They're just doing their thing under the laws of physics. thus the original formation of elementary particles becoming nuclear particles, becoming atoms, and then eventually molecules, then macro, very long, relatively long molecules, which then for hundreds of thousands of years were just all by themselves, with photons banging around among them at extraordinary high temperatures, starting up at incredible numbers, falling down to 5,000 degrees or so, about 380,000 years after the universe began. From then on, it cooled down, the universe did, it got the light, bright light in all directions, changed into darkness in all directions. And then gravitational force took over, pulled material together, formed galaxies, the stars, which suddenly in the dark sky, points of light appeared. And these were things that couldn't yet be stable stars, probably, because the big heavy ones crashed down first and they exploded like supernovae do even to this day, and destroyed the star-like object. Or they may have been so big they collapsed all the way into black holes, or neutron stars, which we've just discovered circling around one another and forming a single object, which generates the gravitational waves that we're now detecting with our amazing gravitational wave observatories. Gravitational waves, by the way, were predicted by Einstein way back in his early work in general relativity. We're on a Friday lecture today, and I'm hoping to talk about Albert Einstein, of course, and I'm so pleased to be working to restore the things that Einstein saw, and then some of them he gets credit for. Relativity, no doubt, he's considered the original architect, saw things which no one else could understand, famously. And as we heard from Richard Feynman a couple weeks ago, Feynman said people had told a story that at one time only 12 people understood relativity, and he put that down by pointing out that, well, there may have been a time when only one person understood it, but 12, because one person was the one who invented it, and that's Einstein. Feynman didn't exactly say, but very quickly others read it and came to understand it. It's not nearly as difficult, although mathematically complex, incredibly complex, mathematically and difficult math. It is nevertheless understandable, and many people understood it, well beyond the 12 that was supposedly the only thinkers in the world who understood relativity. But then Feynman goes on to say, I can safely say, however, that nobody understands quantum mechanics. And that's made Feynman famous and quantum mechanics infamous as something which no one can really understand at all. And it is true that in quantum mechanics today, there's very little agreement on exactly what is going on in quantum mechanics. And there are at least a dozen different interpretations of quantum mechanics, most of which attempt to get beyond the fact that it involves chance, randomness, indeterminacy, which Einstein is the one who discovered it in 1916, just when he stopped working on relativity, his general relativity papers in 1916, he picked up quantum mechanics. I'm going to try to convince you in my work, and my work consists not just of these lectures, but of writing books. And in this case, the book I'm writing now, I'm halfway through, is called My God, He Plays Dice. Einstein's famous remark that God doesn't play dice was his description of a world in which things were orderly and governed by laws, which Einstein had discovered some of them in the laws of general relativity, which advanced beyond Newtonian laws of physics. And the Newtonian laws had been for 400 years the standard, the gold standard of understanding everything, because things followed exactly from causal chains coming from the past, and each object was pushing on the other objects according to the law of gravity and so forth. Einstein changed all that, but he did not like the changes he was making. And all his life, he thought there must be something more than this new quantum theory, which he invented most of the concepts. I'll rattle off those particulars he contributed before the so-called founders of quantum mechanics in the mid-1920s, but I don't want to go into too many details today. Instead, I'd like to pick up on one thing that made Einstein's bad reputation for the most part. It was the work he did in 1935, although he had hinted about it in 27, and 1930, and earlier, all the way back to 1905. In 1935, he published a book, he published an article, which was actually written by one of his colleagues at Princeton University named Boris Podolsky. And quickly after that article appeared in English, Einstein was not well versed in English at that time. He'd come away, running away from Germany and the advance of Nazism and so forth, very much expecting to be killed if he stayed in Germany. And he came out to Switzerland initially and then to Princeton, where he spent the rest of his life. While he was there, Podolsky and another Nathan Rosen, colleague there, wrote up an article which became known as the Einstein-Podolsky-Rosen paradox, a criticism of quantum theory. So EPR, it's known of as in the philosophical and the science philosophy literature. In EPR, in the simplest one-term claim, Einstein asked the question, is quantum mechanics incomplete? Is there something missing? Okay? And I'm going to try to explain that to you, what incompleteness meant to Einstein, and then what it was taken to mean by the founders of quantum mechanics, who were frankly insulted that Einstein was claiming that their wonderful new theory, and it was a wonderful, is today, an amazing theory. Quantum mechanics and what's called wave mechanics version of it, done in the 1925-26 time frame by Werner Heisenberg of the uncertainty principle, and Erwin Schrödinger of the famous Schrödinger cat experiment, which is taught every day to school children. And I'm going to maintain it's basically a scandal, the way in which it's taught, so as to leave people, everyday laypersons, with the impression that quantum mechanics is somehow impossible in some way or mysterious in the extreme. Now, there is a mystery, and I believe that Einstein told us what that mystery is in relatively simple terms, and that the founders just told him, don't think about that. Don't try to look down at what's happening at the quantum level. This, I think you maybe can see, is much like the positivists around since the late 19th century and into the 20th century were saying about understanding the world. Don't try to understand the world. Don't look. You won't understand. You won't be able to see what's going on down at this level. Well, that may have been true at the time. It didn't mean someone like Einstein couldn't think about what's going on at the quantum mechanical level or the atomic microscopic level, and he did think about it, and he saw things that no one else saw. In 1905, he saw that when light waves go out in all directions, they seem to be able to collect themselves at one single spot. As all the energy that may have gone out in a wave in all directions suddenly collects all the energy and appears as a quantum of light. He called it a light quantum. We know that today as a photon. No one has ever fully understood the, quote, mechanism, if there is a mechanism, by which all that energy could have been suddenly collected together. As Einstein saw right away and explained in very good detail in 1909, it appears to violate his principle of relativity, which he also wrote in 1905, in the sense that if the wave went out, light wave went out and filled the room with light, and then we made a measurement, we found a light quantum, a light particle at this one spot. How did all that energy get there instantly without violating the special theory of relativity? That remains, quote, a mystery at some level. I hope to get to the bottom of that mystery. but I will not be able to get to understanding how it is that particles like that photon, that light particle, decide where to go from here to there, the path where it travels from here to there. Einstein said maybe that particle hasn't really traveled to all these other places, but the light energy is out there, and he's worried about the light energy recollecting. But I'm going to show that what we don't know is how and why the particle decides where to go, and that remains the fundamental mystery in quantum mechanics. Now, this story will be told in several chapters, 35 chapters. I'm now writing chapter 17 or 18. I'm happy to say that I'm back getting a little writing done, despite lecturing 5 times a week, which is consuming a bit more time than I thought it might take, and it is slowing down my working on my next books. After Einstein, I will write another book in the Scandal series. My first book was called The Scandal in Philosophy, Free Will, The Scandal in Philosophy. And today, I've written a couple others, but those are not scandals. They're in my Solved series, Great Problems Solved, Metaphysics, Paradoxes and Puzzles Solved. But after I write Einstein, my next book will be called Mind, The Scandal in Psychology, because I find that in the 20th century, among the things they said we can't think about was the mind, right? What we had was the development of behaviorism, and in behaviorism, you can't look and talk about the mind because introspection is not science. It's not, science has to be shared among all thinkers and visible experiments that all can participate in. And we can't all look into everyone else's mind, just into our own minds. That basically eliminated mind. It's like the psychologists lost their minds. After that, I hope to write at least 5 more books in the Scandal series. And one of them will be called Quantum, The Scandal in Physics. Because I hope to show that Einstein was right, that quantum physics, quantum mechanics is incomplete. And whether Heisenberg or Bohr or all the other followers succeeded in convincing most other physicists that quantum mechanics is complete, sadly, it's like kids in a sandbox arguing with one another. Einstein is saying, it's incomplete. And the others are saying, no, 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 this is a complete theory. They were just verbal jousting, quibbling, word juggling. I hope to show. And that's a big task on my part. I'm basically relatively unknown in the field, either in philosophy or physics and quantum physics. But I do believe, I've been working on this over the years, and I do believe I'll put the arguments together which will convince at least some philosophers of science and maybe some physicists to think more about what Einstein was telling us, because he was not the senile old man that the founders of quantum mechanics claimed that he was. Niels Bohr famously argued him down in meetings every day at a conference in 1927, and it's Niels Bohr who wrote the history of that time. We do not hear Einstein's side of that story. I hope to tell that side of the story. So what we have here is my blog. Remember, I'm now developing a bunch of tools, which I'm hoping at some point you will be able to drive around in among them. This is a blog which is called i-phi.org, and every day during the weekdays I write the title of a talk, and I put in a few paragraphs out of my works to explain where we're going. So here's our lecture yesterday on whether the mind reduces to physics, or there's something else going on that emerges. So I hope you'll be able to use this to look back at my earlier lectures. I like to show that once I've got a lecture completed, let's see whether I've completed this one or forgot to do it. No, I don't have my lecture there quite yet. Below each lecture, here's Donald Hebb. I should have a link to the YouTube version of the lecture. So I'm delinquent here today. It's been a busy morning, and I need to put a link to that lecture. But let's take a look at this one on whether quantum mechanics is incomplete. And what I want to do is cut over to another page in which I've written all about Einstein. This page is hugely long, web page, and it has a lot of the specific stories of events, each particular important contribution to quantum mechanics in 1905 and 1909, maybe one there in 1907 actually, one in 1916, another important one in the early 20s, 24, and then major insights into what are called non-locality in 1927, and then entanglement in 1935. All of those things are normally credited to other people. Very sad. I can't imagine almost how someone as important and world famous as Albert Einstein couldn't hold up his end in the arguments and get credit for quantum mechanics, which he should get as much as he does get credit for relativity. Okay, so I'm choosing one person, Paul Dirac, you see here. Einstein thought, let's see, no, I need to go back to this one for a moment. Einstein thought that Paul Dirac, who wrote the Principles of Quantum Mechanics and was the developer of what's our modern mathematical notation for quantum mechanics, and he did it as a young man in the early 20s, at the same time that Heisenberg was in his 20s, same age or so, and 24, 25, and Schrödinger was in his 40s when he wrote wave mechanics. But Schrödinger took the works of Heisenberg's matrix mechanics, or particle mechanics, big emphasis on particles being disturbed by attempts to measure where they are, and Schrödinger had developed wave mechanics. And just within a few weeks of these two theories, which look totally different from one another, but were shown by Schrödinger to lead to exactly the same results. Even though the Schrödinger work, everything was waves. And in the matrix mechanics of Heisenberg, there were particles only. There were then some waves in the form of light, but they had not yet been incorporated into matrix mechanics. And it's really quite surprising that two completely different looking, very different in appearance, math and theoretical predictions should produce exactly the same energy levels in the atoms and the same formulas for how much light was coming out of atoms when they emitted what Einstein had shown were light quanta, later called photons, and Bohr said was a continuous wave. Niels Bohr stayed thinking a continuous wave was the way light was transmitted, because otherwise no one could explain the interference that we talked about in some of our earlier lectures, how it is these light waves going through two different slits produce this strange pattern on the back screen. Let me just click to a page here and remind you that we looked at this. I can take that to full screen right here, and basically on the left, we see what happens when you have one slit open. On the right, two slits are open. And look at that bump on the back side. That's actually a pattern. Here's a negative exposure of where the light is when there's only one slit open, and that light is exactly in line with the slit where the light is coming through. But then there's some of the light goes off in other directions, and some of it interferes with itself, but in this pattern. But if you open a second slit, the original light coming through, which used to land a bright spot right here, there's darkness now. This is amazing, as I tried to point out. How can we explain the fact that when we have one slit and lots of light in the background, landing on a particular spot on the photographic plate right there, how can we explain that keeping that same slit open, the same amount of light going through, okay, and then another slit off to the right with light going through there, And the net of this opening the second slit, which should add light up at the back wall there, it just should add light, it actually erases light right in the middle of where light used to be. That has got to be one of the most dramatic aspects of the mysteries of quantum mechanics, but something we can explain today. Let me then come back to Dirac. I want to be over here and say that Paul Dirac had combined the ideas. Let's see, I need to be on this one, and then come here. Paul Dirac had summarized or combined and really mathematized. He had come up with a different form of expressing mathematical computations to get the values of things with a notation which became our standard today. Paul Dirac had taken these two competing theories and written one which he described in a book called The Principles of Quantum Mechanics. First article right away in 1926, just after Schrödinger, and then in the next few years he put forward this theory. So in 1931, let's see if I've got that right here, and yes I do. In 1931, Einstein said, and maybe I should have this on a screen where I can go with the words. Let's see, that one would be nowhere to be found. Let me just switch to this screen so you can see what I'm working on. I have a lot of tabs up here, so it gets me a little confusing. I'm going to go to i-phi.org. And here we are. And here's Einstein talking about Dirac, and I can help us through this. In 1931, very early, way before his entanglement paper, the Einstein-Podolsky-Rosen, where he questioned whether quantum mechanics was complete, he said, Dirac, to whom, in my opinion, we owe the most perfect exposition, logically, of the quantum theory, rightly points out that it would be probably very difficult, for example, to give a theoretical description of a photon such as would give enough information to enable one to decide whether it will pass through a certain polarizer in its way, or not. Now let me just translate that for us into the two-slit experiment. Dirac is saying, here comes some light, and you polarize it. And polarized light has its wave, its electric vector going up and down in a plane, say, or maybe at an angle, or maybe horizontally. And then you have a polarization, a sheet of polarization. I'll do a demonstration of that maybe next Wednesday when we pick a philosopher or scientist to discuss. We'll go to Paul Dirac, and I'll have a nice demonstration of what he was talking about with those polarizers. Anyway, the question is whether the photon coming down, and Einstein calls it a photon, does he right there? Whether it, to enable one to decide. Oh yeah, photon. Here's Einstein accepting the word, let's see, go back here. He's accepting the word photon, which is pretty interesting. Whether it would do something or not, and it's very similar to when the wave of light goes through the slits, or two slits, whether they will interfere or not. It's probabilistic whether they will or not. It's statistical whether they will or not. So let's go back up to the title. Einstein thought Dirac's statistical theory was perfect. Remember, he said most perfect in the quote we just did. But there was something possibly wrong with it because Einstein had wanted something to be a field theory. Now, what's the difference between a field theory and a particles theory? These are the great contrasting pictures of whether the universe is made up of fields like gravitational fields or light waves. Electromagnetic waves are thought to be an electromagnetic field, and there are many such pictures of the world where there are fields, and then a particle is thought to be, here's this field, and it has values in different places, and maybe at some point it comes into a kind of singularity where it has a very large value, and that may be what a particle is. A particle may be just a space in the field where there's a lot of the field strength, and that looks like a particle moving around in the field. Einstein always wanted a field theory, famously called a unified field theory, where he would unify the electromagnetic field with the gravitational field. The gravitational field is, of course, Newton's work, and it's completely a field theory, although he describes particles like planets going around the sun. And the electromagnetic theory was the work of James Clerk Maxwell. And that theory was a field theory, although in 1899, physicists discovered the electron, which is the facilitating particle that, when it oscillates, sends off waves. And you'll probably remember that the electromagnetic theory of that day assumed there was a medium which was oscillating, that the electric field was actually, because there was an ether in the universe, a kind of matter, not exactly, not physical, not particle matter, but somehow something which was doing the oscillating and could occasionally form a spot which they called the electron. Einstein liked Maxwell's theory, and he thought Maxwell's theory was just the most wonderful thing to integrate somehow with the gravitational theory, and he spent his whole life looking for such a theory. Then his goal of getting a unified field theory would allow him to explain everything with equations that predict values at all points in space. What quantum mechanics seemed to be saying, on the other hand, was that perhaps the light of photons only looks continuous because there are so many photons in normal situations. Now, he studied a situation where there was one at a time landing on a metal plate and ejecting a single electron. We talked about that a little bit. And in those circumstances, Einstein asked, what's the relationship between the light everywhere and a photon? And all he could say, and all Dirac could say, is that there's a statistical relationship, a probabilistic relationship. And Einstein uses the term probabilities, that in those early studies he did, 1909, it appeared to him that maybe that the field, which looked like a light wave field, was only giving us the probabilities of where photons would be found if you went and looked for them. And that might also be true of matter in general. Maybe the idea that we have matter fields is because we have lots of particles, and it's the distribution of the particles that averaging over them gives us the fields. So let's come back to this one and scroll down a little bit. So 4 years later, after this quote in 1931, this was an article which you can click away from my blog or find this link on my webpage, or I think I also have it on my Dirac page here somewhere. We'll skip that for a moment. This is a very interesting paper because it's talking about his own ideas of how to describe physical reality. Now remember, in 1931, Einstein was saying he would like to find an objective reality that is visualizable going down there below, the ultimate reaching the things themselves, little particles themselves. And he thought Maxwell had a big influence on physical reality. Then 4 years later, got a typo here, in the infamous EPR paper we're just talking about, Einstein said quantum theory appears to be incomplete. He believed that quantum theory, as good as it is, and he never saw anything better, I maintain, and I think he made this very clear. He saw nothing better, but that it was incomplete because it is a statistical theory, and its statistical predictions, which were phenomenally accurate, and the limit of large numbers of particles, you now get this appearance of continuity, and the accuracy in terms of what are called significant figures is terrific. It goes out today to something of the order of 14 or 15 decimal places in the predictions that quantum mechanics makes about the world. It is extraordinarily accurate about ensembles, large collections of particles, but it can tell us nothing except some probable outcomes, one particle at a time. And so he called them ensembles, but as he pointed out, it tells us nothing but probabilities about an individual system. And in 1935, in this EPR paradox paper, it seemed to him that the theory of two particles which are somehow start out in the center and separate, they have been entangled by this quantum theory, such that if you make a measurement of one of them, it instantaneously influences the value of the properties of another one, however far that one may be, okay? However far away, and that again goes back to his insight in 1909 and probably in 1905 that something looked to be going on that violated his principle of special relativity. My goal with the book and these Einstein lectures every Friday is to see past that problem, that Einstein was wrong about influences, or what we could call information, traveling faster than the speed of light, because his relativity principle does tell us correctly that nothing goes faster than the speed of light, including any kind of signal. All signals transfer or are transmitted at the speed of light. That's going to be a task for you and for me to see if I can get the stories together about how we think about this, and the fact that the measurements here perfectly correspond in some way to what goes on at this other particle, which is separated and now gone to great distances apart, and yet they seem to be correlated in ways. I hope I'll explain that to you and see that we can get around his concerns about the velocity of light. So let's again read what's on this blog page. The entangled particles predict faster than light correlations of properties between events when they are in a big space-like separation. He mistakenly thought this violated his theory of relativity. Although this was the heart of his famous EPR paradox paper in 1935, we shall see that Einstein was already concerned about faster than light transfer of energy, and that he saw spherical light waves, the ones that in his first paper in 1905 going out in all directions, collapsing. And that's related to the modern puzzle or mystery of the, quote, collapse of the wave function. Schrodinger's wave function has values in lots of places, and then suddenly it seems to not have values, as if they've collapsed. Nothing physical is collapsing. Nothing actually is moving. It's just that the particle now shows up somewhere, and that does mean that the probability of it being somewhere else at this moment that it's measured goes to zero. But that's just a change in probabilities, and it's not a material signal that's come from where it might have been to where it winds up being. And so he saw waves collapsing instantaneously in Einstein's first paper on quantum theory. Now, in most general histories, and in the brief histories included in modern quantum mechanics textbooks, and I've looked at, I'd say I have about 40, 50 quantum mechanics textbooks at the moment, and I've gone through them all carefully, and I find several of them have mistakes about who did what, which is quite interesting. In other words, historians of science, when they are scientists, tend to sort of tell you the story they learned, the one they learned when they went to graduate students and studied decades after the case, in many, decades after the original development of quantum mechanics, and they write the story that has come down mistakenly. One big one is that many physicists, great prominent physicists, think that Max Planck was the one who quantized energy. So the light quantum idea, which I will show, and most people who have looked at all closely know that Einstein quantized light energy into what became photons. In fact, I will show that Niels Bohr fought against this idea from the 1900 time frame when he put it up and he invented the quantum of action in order to explain radiation theory. He did not believe that that radiation came in packets or quanta or photons. Until the 1920s, he became seriously convinced. He probably started to take it seriously. Well, Niels Bohr definitely objected to it, attacked it until the middle 1920s. Probably Planck came around to talking about it and mentioned it in his Nobel Prize in 1921. So sometime in the early teens, probably, for Planck. But I'm amazed that so many books don't know those stories, and that story needs to be told in order to restore Albert Einstein's reputation as not just a great relativity theory, but a great quantum physicist. Indeed, in my mind, the greatest of all of them. Heisenberg and Schrödinger and Dirac put the math together so that we could do calculations. And that's very important. If you're an engineer, if you're a quantum mechanical engineer, you know how to do calculations. That's thanks to Dirac and Heisenberg and Schrödinger and a large group in the late 20s. They deserve all the credit for that. But they never had the concepts of quantum physics that Einstein saw so early. And they never explained them any better than he had, as we will see. So I write in most general histories and in the brief histories included in modern quantum mechanics textbooks, the problems raised by Einstein are usually presented as having arisen after the late 1920s, when the founders developed their so-called Copenhagen Interpretation of quantum mechanics. And I'll try to give you a good idea what that theory is. It's mostly, don't look, just calculate. Richard Feynman liked to say, shut up and calculate. Anyway, modern attention to Einstein's work on quantum physics often starts with that EPR paper. Now, it's very strange, but the reason is because that was the time when the mysteries of non-locality, of non-separability, and entanglement are first understood by Einstein's opponents. Now, at that time, they thought they didn't understand what he was talking about. Niels Bohr said, Einstein got up and presented the situation at a Solvay conference in 1927, in which he saw this, what's called today, non-locality, non-local effects. Apparently what's happening here influences what's happening there at faster than the speed of light. And when Einstein sat down, Niels Bohr stood up, and I have it on my Einstein page. He basically says, I don't know what Einstein's talking about. And to add insult, as they say, 1935, 1949, 14 years later, Niels Bohr will tell us what Einstein said in 2027. It's 22 years later. He will write about this event. Niels Bohr will write about it mistakenly, but again show that he doesn't understand what Einstein was talking about. And that's because the thing that Einstein saw, which is now called entanglement, and it's at the heart of a lot of modern theory, including quantum computing and quantum encryption used in communications around the world, and using strange effects that John Bell described would be the case if quantum physics was true, as Einstein was describing it. It would have these certain phenomena which could be studied, according to Bell. And Bell predicted that if you did the experiments and it came out the way Einstein wanted things to be, he would have achieved being right. Bell wanted Einstein to be right, wanted Einstein's work to show that quantum physics with its strange statistical behaviors was false. But then when French scientists, Alain Aspect and Americans in a couple of places started doing these experiments, the Bell tests of Bell's theorem, strangely or amazingly to Bell especially, it turned out what Einstein was worried about was actually happening. And now Einstein is thought of sometimes as being behind this. Certainly Schrödinger was behind it. And he's more famous for this, EPR stuff, entanglement, non-locality, non-separability, even though that was ignored for the most part. After that 1935 paper, people said Einstein's lost it, and they went on. But 1970s, 60s, 70s, 80s, he's back big time, just like his predictions of gravitational waves have been confirmed. Anyway, physicists today think of quantum mechanics as beginning with the Heisenberg particle formulation and his uncertainty principle and the Schrödinger wave formulation. And here we have the two sides of this wonderful, mysterious idea or question. What is it? Is it a particle or is it a wave? And there are dozens and dozens of YouTube videos. I think I will show some of them to you in future discussions of wave-particle. And everyone wants to talk in this odd way that we can't understand how it can be a wave, how it can be a particle. Is it both at the same time? Is it neither one? Is it something else that could be explained by some future intelligent physicist? We are lucky enough, I hope you and I, we will be able to see that Einstein actually saw what was going on. Because he didn't like it, okay, he was thought to be clueless and out of touch, and he was disregarded. My work with this book, I hope to get this thing out sometime in the spring, and still lecture every day, 5 days a week. We will restore Einstein's reputation. Okay, let's just open this up a little bit bigger here and follow this story down. So the popular image of Einstein after the Einstein-Podolsky-Rosen, the popular image is either in the role of a critic who's trying to expose fundamental flaws in the new quantum mechanics, or as an old man who simply didn't understand the new quantum theory. And both these images of Einstein are seriously flawed, as we shall see. So maybe I should take a moment. Let's see, we've got about 10 minutes more to the lecture today. But let's just say that all the Copenhagen people, and that includes Bohr, Heisenberg, Max Born, Pascal's Jordan, Wolfgang Pauli, incredible, great people, they focus on his failed attempts in his debates with Bohr to challenge the uncertainty principle or something about the Copenhagen interpretation. And EPR is described as failing to show that quantum mechanics is incomplete. They boast that they are complete. And I believe this is just verbal quibbling, and argue that quantum mechanics is indeed incomplete in that it cannot predict simultaneously the position and the momentum of a particle, nor can it predict the real path of a particle between measurements, okay? And by that, we noticed in the two-slit experiment, or even just one particle in the original Einstein, or one small amount of light going into that volume he saw in 1905, and then showing up, okay? It comes in and it seems to go in all directions, and then it shows up at this one plate. And each one at a time is a different place. Clearly there's something statistical or probabilistic going on. He always saw that. But at that theory of quantum physics cannot predict nor measure the real path, okay? Let's quote that one right here. The real path of a particle between measurements. If you measure the particle in between two possible measurements, one here and then one there, if you measure it in the middle, you now start a new path. You now know something, and that destroys the interference pattern in the two-slit experiment. It's a bit subtle, but Einstein saw that you cannot know the path. But he said, is it possible that the path exists, that the particle has a path between measurements, but it's just that we cannot measure it because our touching it, Heisenberg says, disturbs it. Einstein says our measuring it gives us knowledge of where it is, and then it can't do interference with other particles. That's where we're going to be. But the key thing from certainly in the mid-20s, when he looked at quantum mechanics, he saw that it was a statistical theory. And quantum mechanics is only a statistical theory. Its results are only confirmed by large numbers of identical experiments. And the continuous aspect of light radiation or of matter is just because we're averaging over large numbers of discrete particles. So very few histories point out that he's the one who discovered all of these things and so forth. I think I wanted to just take a quick look at Paul Dirac, and he is somewhere here. Let's try this one. This is my web page on Dirac, and you see I've put on this page, let's just take us there, full screen. Dirac wrote a textbook called The Principles of Quantum Mechanics in 1930. So that's 4 years after he first showed that wave mechanics and particle mechanics or quantum mechanics were the same theory. Just an incidental personal note, Harvard Library, Widener Library, said that they had a copy of Paul Dirac's 1930 book. I have worked for years from the 4th edition, which came out in 1956 when I was at Brown, studied quantum physics at Harvard, got my PhD in the 60s, and the 4th edition was the best textbook on quantum mechanics, bar none. Although I also studied Albert Messia's quantum mechanics, big 2-volume thing, which taught us how to do all the calculations. Dirac, especially in the first chapter of the Principles, really set out the statistical nature of quantum mechanics. And Einstein read that book. In 1931, that book by Dirac had just come out, and Dirac had published a half-dozen extremely critical papers establishing our modern views of quantum physics. He didn't get everyone to agree with one another, despite doing a fantastic job giving us a mathematical theory, a fundamental theory of the equations we need to use, starting from Schrodinger's equation, but also then showing how to evaluate what are called matrix elements in the Heisenberg matrix theory and how we get values for measurable things, okay? So in 1931, Einstein remarked on his work, and that's where we began, but let me just home in. I added this quote right here. Dirac, we owe the most perfect exposition, and so forth. So I've got that as a reference back to Einstein from my Dirac page, and I'm going to show in a future talk, we don't have time today, how Dirac explained one of the mysteries of quantum mechanics, that you only can predict statistically what a measurement is going to be. And I just wanted to mention, this week I went on my Harvard Widener Library online listing of all the books, and there was Paul Dirac, 1930, Principles. Now that's not an easy book to find. I went on to Amazon and on to abebooks.com, which is a wonderful place to get books to add to my library. I thought, why don't I add a copy of the 1930 version? I do have his papers from 1926, but Dirac did a wonderful job explaining quantum mechanics, and if you wanted to start at the beginning, it does require a little bit of math, but boy, the principles are so clear there. Without the math, you would read the first chapter of this book. In fact, I have put the first chapter of Dirac's 4th edition on my website on Paul Dirac's page. I have scanned it in with my scanner, converted it to HTML, and I make it available to researchers, to anyone like you who want to know deeply what's going on, rather than read a popular Scientific American article, which is just putting up the pizzazz and flash of mysteries and not really teaching much, in my view. They're beautiful, these popular science magazines, but they're very limiting in terms of our ability to know what's going on in the world, in my opinion. So I went down to Widener Library and went into the shelves and got to 399.30.9, and there's no Dirac book there, turned out. So I had to go to the librarian and said, I came in for this special book. And I told her, this is extremely rare. The cheapest one I can find to buy as a used book is $1,500. Wow. And There's another copy available which has Boris Podolsky's name in it. That's the Boris Podolsky, the P of EPR. This was his book at Princeton. And says the bookseller who has it, says, not only does it have his name, it has marginal notes throughout on what he's thinking. So clearly Podolsky was well educated and had read Dirac, which is a good sign. Einstein thought he didn't understand the quantum mechanics and had written a very misleading description of Einstein's physics. So there's an interesting story. And by the way, the price on the Boris Podolsky edition, in case you happen to be someone who likes to collect things that are great investments, like artworks, is $5,500. You get the copy of this Dirac book, including his description of the polarizers and so forth, for $5,500. Okay, so let's go back to Dirac's book for just a moment. Oh no, that's the wrong one. I want this one. No, that's not the right one. Okay, I want to. Where do I want to go at this point? I guess we more or less followed through on the whole pre-presentation that I put up on my blog. We've looked briefly at Dirac's three polarizers. And maybe we'll take a quick look back at Albert Einstein, which is here. And I want to just show you where we are in the Einstein page, just briefly. Here's the opening of the page, and I explain why we need Einstein, because he's the one who saw indeterminism. And to me, without chance, without uncertainty, without a statistical nature to the universe, everything would just be the one possible way. So those who say the future can only be one possible future would be right. But for the work that Einstein did especially 1916, when he showed that there are possibilities out there, and here we are. And those possibilities give us an open future. So just a brief glimpse down my page as we wind up our lecture for today. Here's a statement that says Einstein saw the random collapse way back in those early years. They thought they had discovered that. And this is basically the words that I am now putting into my book. So here's his work in 1905 on the light quantum hypothesis, which was definitely different from Max Planck. Here's the idea that a particle of light came in and it would kick out an electron in 1905. Here's his arguments. There are both waves and particles, and the connection between them is probabilistic in 1909. And in 1909, we have this, I put his words together into this story of how an electron can come in, go off in all directions as light, which we now would call a photon, and that photon could hit another plate and eject an electron. It's amazing insight by someone which was not accepted for years and years. And then in 1916, Einstein works out the way light comes out of atoms and gets absorbed by them later. And it goes on and on. He discovers irreversibility and the fact that there's statistics. I'll describe all this for you later in future lectures. And in the meantime, we probably ought to sign off for today and say that I appreciate your being with us. Let me put up my email address in case some of you would like to contact me with questions about Einstein or about the other day's topics. On Monday, we'll come back to some selection from my book on great problems of philosophy and physics, which, as I always remind you, is available free online, downloadable as a PDF from informationphilosopher.com/books. And I think that's about what we want to do for today. I've gotten better and better at ending my YouTube lectures and Facebook by cutting it off just a few seconds before we are cut off by channel 9 in our local cable television system. The public access station, CCTV. So I'll just say thank you very much, and I will cut off this lecture in just 5 seconds. Thank you all.